Microsoft's Large Action Model (LAM) represents a significant leap in artificial intelligence designed not just to generate text but to perform tangible tasks within the Windows environment. Unlike traditional language models, which excel at producing natural language responses, LAM bridges the gap between textual output and direct interaction with software. It interprets user instructions, generates detailed step-by-step plans, and executes those plans across Microsoft applications such as Word, Excel, and PowerPoint. This innovation shifts AI capabilities from mere text generation to practical task automation. The creation of LAM involves a multifaceted training approach that combines supervised fine-tuning, imitation learning, and reinforcement learning. These techniques endowed LAM with the dual ability to plan tasks and execute them in dynamic settings, simulating human-like interactions within software interfaces. To provide the necessary training data, Microsoft compiled a vast collection of task descriptions and real-time action sequences. This data was sourced from a variety of platforms, including official software documentation, WikiHow articles, and Bing search queries. To transform raw text into structured data pairs, the team leveraged GPT-4. These pairs contain instructions and their corresponding actions, ranging from basic tasks like changing fonts in Word to complex multi-step operation involving user-defined styles, form filing, or intricate formatting. One particularly innovative technique used in training process was data evolving. In this method, GPT-4 added layers of complexity to simple tasks by introducing new conditions or instructions. This iterative refinement process enabled the development of over 76,000 task plan pairs, representing a wide range of scenarios. While generating written instructions is relatively straightforward, converting them into actionable steps in a Windows environment posed a unique challenge. Microsoft addressed this by creating task action data, which paired textual plans with actual user actions such as mouse clicks, keyboard inputs, or function calls. For example, an instruction like highlight text would correspond to selecting text in Word and clicking the text highlight color button. This approach allowed the AI to connect abstract plans with real-world actions. The development of LAM involved four primary phases. The first phase, Microsoft started with a foundational model called Mistral 7B. This model was trained to generate coherent task plans for various scenarios, such as inserting images or changing fonts in Word. The result was LAM-1, capable of outlining tasks but not yet able to execute them. The team used 2,192 successful examples labeled by GPT-4. These examples demonstrated how to perform specific tasks within Word's interface. By imitating these examples, the model evolved into LAM-2, gaining the ability to generate action steps and replicate user-like behavior such as selecting menu items or typing text. In the third phase, LAM-2 was challenged with tasks that GPT-4 had previously failed to complete. By experimenting with solutions, LAM-2 discovered new ways to handle these tasks, contributing 496 additional successful action sequences. Retraining with this new data produced LAM-3. Finally, in the fourth phase, the team introduced a reward model that assigned positive scores to successful steps and negative scores to failures. Using reinforcement learning, the model optimized its decision-making process, culminating in LAM-4. This version systematically applied lessons from previous successes and failures, achieving superior performance. To assess LAM's capabilities, Microsoft conducted both offline and online evaluations. The offline test involved 435 tasks in Word, ranging from opening a blank document to advanced formatting and data manipulation. The results showed consistent improvement across development phases. LAM-1, trained only on textual instructions, achieved a 35.6% success rate. LAM-2, enriched by GPT-4 examples, reached 76.8%. LAM-3, boosted by self-discovered solutions, climbed to 79.3%. LAM 4, enhanced with reinforcement learning, achieved 81.2%. In comparison, GPT-4 operating in text-only mode scored 67.2%, while smaller GPT-4 mini model managed 62.3%. Even GPT-4 with visual input achieved only 75.5%, highlighting LAM's superior performance in handling Windows-specific tasks. The online evaluation tested LAM in a live Windows environment with Word running on dedicated virtual machines. Here, LAM 4 demonstrated a 71% success rate, completing tasks in an average of 5.62 steps, with each step taking approximately 5.41 seconds. By contrast, GPT-4 with text-only input achieved 63% success, requiring significantly more time, approximately 86.42 seconds per task. Even GPT-4 with visual input, which performed better at 75.5% success, was slower than LAM, often taking over 9 seconds per action step. These evaluations underscored the value of specialized training. Unlike general-purpose models like GPT-4, LAM excelled in a narrowly defined domain due to its focused training and iterative data collection. Its ability to perform actions, not just generate instructions, made it both faster and more accurate in Windows-specific tasks. To bring LAM's capabilities to life, Microsoft integrated into two Windows-based agents called UFO, or Unified Framework for Operations. UFO scans the graphical user interface, or GUI, to identify elements like buttons, text fields, and menus. It then provides this information to LAM, which determines the appropriate actions such as clicking a button or entering text to execute a task. UFO performs these actions while tracking progress, ensuring that the task is completed accurately. This real-time interaction sets LAM apart from older models that merely generate textual instructions. For example, LAM can open Excel, copy cells, navigate to a website, and paste the data into an online form, all autonomously. Its ability to perform across applications opens new possibilities for AI-driven automation, enabling more complex workflows than ever before. Despite its impressive capabilities, LAM's development is not without challenges. One significant concern is safety. If the model misinterprets a command or deviates from the intended task, the consequences could be serious, especially in sensitive domains like finance or healthcare. To mitigate these risks, the development team has implemented error-checking mechanisms and may require human verification for certain actions. Another challenge is scalability. Extending LAM to other operating systems such as Mac OS or mobile platforms requires new datasets specific to those environments. Collecting and labeling this data is a time-sensitive process. While techniques like transfer learning and multitask learning could help, these remains areas of ongoing research. LAM's development represents a shift in AI's role from passive assistant to active operator. By executing tasks rather than merely suggesting solutions, LAM paves the way for more autonomous and efficient workflows. Its success in the Windows domain suggests that similar models could be developed for other platforms and applications. Microsoft's researchers detailed their work in their technical paper titled Large Action Models from Inception to Implementation. The paper outlines the training process, data collection methods, and the architecture of the UFO agent. It also highlights the ethical considerations surrounding AI-driven automation, including issues of accountability, bias, and the potential for misuse. As AI continues to evolve, models like LAM signal a new era of capability. By combining specialized training with real-time interaction, LAM demonstrates how AI can move beyond generating text to performing meaningful actions. While challenges remain, the potential for automation and efficiency is immense. What do you think about this rapid progress in AI? Is it an exciting step forward or a cause for concern? Share your thoughts, and as always, thank you for watching.